In this video, we're going to prove the theorem that every natural number n is either even or odd, but not both. So just recall a couple of definitions. A natural number n is even if there's a natural number k so that n is equal to 2 times k. We'll say a natural number n is odd if there's another natural number k so that n is equal to 2 times k minus 1. Now in some books you'll see this definition of odd written as n is odd if there's a k so that n is equal to 2k plus 1. The reason we take it to be 2k minus 1 is that we're working in the natural numbers where we don't have 0. And so in order for 1 to be one of the numbers that gets swept up in the definition of odd, we need 2k minus 1. Because then we can plug in 1 for k, and we'll get 2 times 1 minus 1, we'll get 1. 1 will be an odd number, as it should be. Whereas if we had 2k plus 1, we don't, since we're only in the natural numbers, we don't have 0 to stick in there. Okay, so this is just an artifact of our definition of the natural numbers. Once we start working in the integers, those two definitions of even and odd, of odd numbers are equivalent. So in the proof of this theorem, we're going to use the following facts about the natural numbers. We'll use the discreteness of the natural numbers, which states that if m and n are natural numbers and m is between n and n plus 1, then actually m has to equal n, or m has to equal n plus 1. There can't be anything between a natural number and its successor. We'll use the subtraction property of the natural numbers. So if n is less than m, then there's a natural number k so that m is equal to n plus k. You might call k the difference between m and n. We'll use two of our cancellation properties for the natural numbers. For addition, if n plus k is less than m plus k, then m is less than n. And for multiplication, if n times k is less than m times k, then n is less than m. We'll use trichotomy at one point in the proof. Recall trichotomy states that if n and m are natural numbers, then exactly one of the following relations is true: n is less than m, or m is less than n, or n is equal to m. And the proof really relies on the division algorithm. So the division algorithm states that if n and m are natural numbers with n less than or equal to m, then either there's a natural number q so that m is equal to n times q, or there are natural numbers q and r so that m is equal to n times q plus r, and r is less than n. So here in division situation, m would be the dividend, n is the divisor, q would be the quotient. Okay, so the first alternative there would be where n evenly divides m and q is the quotient. And then the second alternative would be where n does not evenly divide m. The quotient is q, and the remainder r is smaller than the divisor n. So we'll use all these facts when we are proving that every natural number is even or odd, but not both. Okay, so just to restate our theorem before we start proving it, if n is a natural number, then n is either even or odd, but not both. So to start the proof, we'll do it in 2 steps. In step 1, we're going to prove that every natural number is either even or odd. And in step 2, we'll prove that no natural number can be both even and odd. So let's start with step 1. We're going to prove that every natural number n is either even or odd. So let's let n be a natural number. Okay, now since n is a natural number, it's greater than or equal to 1. In particular, it's equal to 1 or greater than 1. So let's consider each of these two cases separately. Let's take case 1 as the case where n is equal to 1. Well, that case is easy, because in that case, we can write n as 2k minus 1, where k is equal to 1, as I discussed above. So that means that 1 fits the definition of odd. So if n equals 1, then n is odd. And that takes care of case 1 of step 1. Let's look at case 2 of step 1. Here, let's suppose that 1 is strictly less than n. Now, since n is discrete, we know that n can't be between 1 and 2, all right? So it could be 2, but it might be bigger than 2. So discreteness of the natural numbers here implies, along with 1 being strictly less than n, that n has got to be greater than or equal to 2. So we'll apply the division algorithm with n as the dividend and 2 is a divisor. So according to the division algorithm, maybe 2 evenly divides n, in which case there's a natural number q so that n is equal to 2 times q. Or maybe there are natural numbers q and r so that n is equal to 2 times q plus r, where the remainder r is less than the divisor 2. All right. So now we have two subcases of case 2. Let's consider each of those separately. Let's look at the first case where 2 evenly divides n. So there's a natural number q so that n is equal to 2 times q. Well, this case is easy too. That exactly means that n is even, so we're done with that case. So let's look at subcase 2. So here 2 does not evenly divide n. So we're supposing that there is a quotient q and a remainder r, so that n is equal to 2 times q plus r, and r is less than 2. Now we're going to apply discreteness of the natural numbers again. Since r is less than 2 and n is discrete, that means r has to be less than or equal to 1. It can't be between 1 and 2, so it's got to be less than or equal to 1 if it's less than 2. But of course we know that 1 is the minimum natural number, so r would have to be 1 in this case. So if r is 1 and n is equal to 2q plus r, then of course n is equal to 2q plus 1. Now 2q plus 1 is almost our definition of an odd number, but not quite. Remember, our definition of an odd number is it's got to be of the form 2 times something minus 1. Alright, and so we just do an easy little shift to get it to fit the form that we need over the natural numbers. Notice that 2 times q plus 1, 2 times the quantity q plus 1 minus 1 is equal to 2q plus 1. And so that little shift there allows us to say that n is of the form 2k minus 1, where k in this case is q plus 1, and the 2k minus 1 form is what we defined as being an odd number, so we can conclude that in this subcase of case 1, n is odd. Alright, so that finishes case 2 of step 1, and so we're finished entirely with step 1. We've showed that in every possible case, every natural number is either even or odd. Okay, but we haven't shown that no natural number is both even and odd, and so that's what we're going to do next. So to finish the proof, we're now going to show that no natural number n can be both even and odd at the same time. How are we going to do that? Well, let's assume n is even. Then of course that would mean there's a natural number k, so that n is equal to 2 times k. Let's also assume that n is odd, so that means there's some other natural number k prime, so that n is equal to 2k prime minus 1. And since 2k and 2k prime minus 1 are both equal to n, that means they're equal to each other. So 2k is equal to 2k prime minus 1. Alright? So, in other words, 2k is the predecessor of 2k prime. In other words, 2k prime is larger than 2k. And so we'll apply our cancellation property for multiplication to conclude that k prime has got to be larger than k. Right? Now, if k prime is larger than k, we can apply our subtraction property of the natural numbers to find the difference between them. So there's some natural number s, so that k prime is equal to k plus s. Now we're going to rewrite the fact that 2k prime minus 1 equals 2k. We're going to rewrite that as 2k prime is equal to 2k plus 1. And that's going to allow us to use the distributive law. So 2k plus 1 is equal to 2k prime. K prime is equal to k plus s. So 2k prime is 2 times the quantity k plus s. And we distribute the 2 through, we get 2k plus 2s. Okay. So that means that 2k plus 1 is equal to 2k plus 2s. Alright, 2k plus 1 is equal to 2k plus 2s. So we use one of our cancellation properties for addition over the natural numbers, cancel the 2k on both sides, and conclude that 2s is equal to 1. But that's clearly impossible. We can't have that. We know that 1 is strictly smaller than 2, and 2s is greater than or equal to 2. Okay, s is greater than or equal to 1. So in particular, we now have a problem. Alright, so we've just proved that 1 is equal to 2s up on the previous slide. but we know just from basic considerations that 1 is less than 2s. And so that means we have a contradiction to trichotomy. Okay, according to trichotomy, only one of the inequality or equality relations hold. So we have a contradiction here. So our assumption that n is both even and odd leads to a contradiction. And so we conclude that n cannot be both even and odd. So we proved in step 1 that every natural number is either even or odd. And then we have completed the proof here in step 2 by showing that no natural number n can be both even and odd. And that finishes the proof. Thanks for listening.